The headline for Ornith 1.0 promises a future where AI agents improve themselves, but this narrative hides a dangerous engineering reality. When an autonomous system designed to optimize its own code lacks explicit stop conditions, it does not become a productivity hack. It becomes an infinite loop waiting to break your continuous integration pipelines. The core conflict is not about model accuracy or benchmark scores. It is about architectural stability and the risk of resource exhaustion in any environment without strict guardrails. Today, we connect that hype to the specific trade-offs that determine whether this tool builds software or locks down your entire build server indefinitely. To understand why Ornith 1.0 behaves differently, you must look at how it handles self-improvement through reinforcement learning. Unlike standard models where a human usually intervenes when an error occurs, Ornith uses RL to jointly optimize solution rollouts and search scaffolds. This allows the agent to generate its own future logic without waiting for human intervention loops. While this drives high benchmark scores on verified datasets, it removes the hard stop mechanisms required for automated tasks in production environments. The model assumes that generating better code is always possible, but it does not account for scenarios where no solution exists within a reasonable timeframe or resource budget. This mechanism creates a specific failure mode known as a tool loop. In practice, an agent generates code, detects errors through compilation failures, and immediately triggers a regeneration attempt to fix the issue. Without explicit termination conditions in the source logic, this cycle repeats indefinitely. The model treats every error as a solvable problem requiring more computation, rather than a signal that the task is complete or impossible. Community reports from the repository confirm that agents frequently get stuck in these repetitive cycles rather than completing tasks efficiently. This turns a productivity helper into an infinite loop generator if not manually wrapped with safety checks by the engineering team. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The data behind this behavior highlights the immense computational cost of running such unbounded processes. Benchmarks indicate that running the full 397B MOE variant requires massive compute resources to even attempt these self-improvement cycles effectively. Specifically, evaluations averaged over 5 runs, utilized 32 CPU cores, and 48 GB of RAM per instance, with a hard timeout set at 4 hours just to prevent total system lockup. Without these artificial constraints imposed by the operator, agents enter recursive states where they generate code that triggers further generation attempts indefinitely. The trade-off is stark. You gain higher benchmark scores only if you accept that the model will consume all available resources until killed manually or by a hard timeout set from outside the agent itself. Comparing performance metrics reveals why this distinction matters for your infrastructure planning. Ornith 1.0 397B achieved a score of 82.4 on SWE bench verified compared to Qwen 3.5's 76.4. This represents significant progress in automated reasoning capabilities, but it comes at the cost of requiring 32 CPU cores and 48 GB of RAM per instance with no inherent stop condition built into the model logic. Even smaller variants carry risk. The 9 billion parameter version consumes approximately 5.6 GB of RAM locally, yet relies on self-repair loops that compile code, detect errors, and regenerate without explicit termination conditions in the source logic. The core danger lies in infinite loops where agents frequently get stuck in repetitive tool loops, creating unbounded production hazards rather than streamlined workflows. Beyond resource consumption, there is a reality check regarding missing components and hallucinated endpoints found in community discussions that proves this technology remains experimental. Critical parts of the promised architecture are often absent or lack implementation details for open-source deployment. For instance, while documentation mentions a 31 billion dense model to bridge performance gaps, it was notably absent from initial releases on major hosting platforms like Hugging Face. Open AI-compatible endpoints also lacked full implementation details in early iterations, leaving developers without clear integration paths for standard workflows. These missing pieces suggest that the tech is still experimental and not production-ready for autonomous agents operating without constant supervision. The repository currently holds 699 stars and 61 forks on GitHub as of recent activity, indicating strong interest but also active debugging by users encountering these exact architectural gaps. The engineering verdict requires a shift in how we view autonomy in software development pipelines. You do not need to ban the tool or ignore its capabilities. Instead, you must mandate architectural guardrails before turning it loose on your codebase. The mental model shift required is that autonomy without guardrails equals production instability. Engineers must stop viewing self-improving models as magic bullets and start treating them as unbounded processes that require the same rigor as legacy code. This means implementing timeout enforcement, resource capping, and loop detection mechanisms outside of the agent itself. You can use Ornith to generate high-quality solutions, but you must build the cage yourself before turning on the lion. The self-improvement feature is not an upgrade. It is a liability in automated pipelines unless architected with strict boundaries that prevent infinite recursion from consuming your entire infrastructure. The path forward for practitioners involves accepting these risks as part of the cost of adopting cutting-edge autonomous agents. When you deploy Ornith, you are deploying a system that assumes infinite resources and perfect problem-solving capabilities until it hits its hard limits. Your job is to define those limits before they ever become critical failures in your CI/CD pipeline. By treating self-improvement as an unbounded process rather than a productivity hack, you protect your systems from the very risks that make this technology so powerful yet dangerous. The future of autonomous coding depends not on how well these models learn, but on how effectively engineers can constrain them to work safely at scale. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.